It's in other words, evolution is a evolutionary theory is a process of discovering the truth. But evolutionary theory is a product of science. It's a product of scientific investigation and deduction, from the general to the specific, or from the specific issues to the general concepts. And because it's based on science, it has an expiration date. So every single scientific fact has an expiration date. And no matter how long it's been around, all of the scientific facts have expiration dates. And anyhow, it would be those of you that are interested in this topic of evolutionism versus creationism and the division that it's caused in our culture should read the Humanist Manifesto. Now, Christians, the church, that is, the church in the U.S. has been actively engaged in the last, I'd say 30 or 40, 50 years in fighting against evolutionary theory, and especially fighting against evolutionary theory being taught in the public school. Now, the public school, so this battle between the public school administration, which is a branch of the government, and Christian church, that contention is really an artificial issue to be fighting over evolutionary theory, because the real issue is that the schools, that everything that is taught in public schools is consistent with secular humanism. And secular humanism is really a religion. It's a belief structure, and the belief structure is based on there is no God. So that's the premise, that God is a product of man's imagination, and that it's caused all kinds of problems, and we just need to get rid of the whole concept. So, but you see, you can't prove that God doesn't exist. That's an irrational fallacy to try to prove that something doesn't exist by trying to find it and failing to do so. That is not proof that something doesn't exist. So you see what has happened in our culture is that there's this Christian philosophy of scientific creationism, where many people are teaching that evolution is a lie, and that it is an attempt to displace Christianity. Well, evolutionary theory is not an attempt to displace Christianity. Evolutionary theory is a scientific theory. What is trying to replace Christianity is secular humanism. Now, as long as Christians focus on evolutionary theory, it's going to be a useless battle. So if anyone is interested in dealing with this issue, then we're going to have to deal with the fact that secular humanism is basically a religion. It is a faith structure, and it has complete control of the public school curriculum and the college curriculum. And so all of the truths, or the imperatives, the important principles of existence that are being taught in the public schools, K through 12, and in the colleges, the secular colleges, is based on secular humanism. And that's what we should be dealing with. And I think if somebody wants to battle this, they could probably battle it pretty successfully by ignoring See, what's happening is secular humanism is putting evolutionary theory out there for us to contend with. And we can't contend with evolutionary theory because it's not a faith structure. It shouldn't be. You know, some people believe in it, but it's a theoretical construct. It's not a faith construct. Whereas secular humanism is a faith construct. And if you haven't heard of this of secular humanism, it would really be good for you to read the Humanist Manifesto. You can find it on the web, and read the associated documents. It'll take a while. You know, it's some reading, but it's very enlightening. It exposes the actual gist of what's going on behind the scenes in this controversy. So, so Bob, that's sort of an introduction to this. Yeah, I don't know if anybody has a question or something they'd like to interject. Or Bob, do you have anything to add to that?
Well, last week you talked about how you believed at one time that science could reveal truth, but you came to a place and you shared with us one of the experiments that you did, that you came to the place where you realized that science could not reveal truth. And that was a pretty profound testimony. And we have a few new people here today, but I think it would be good just to give a brief summary of that, because when we talk about the science versus faith battle, which is really a false dichotomy, what we're really talking about are two completely different worldviews, and it's viewing science in a way that it's impossible for science to completely do what you had hoped it would do in revealing truth.
Yeah, and you know, I've been thinking that the issue of truth is something of a distraction, if we use the word truth. A lot of times in my biometry class, I will tell them that I'm a Christian, and then I'll say, you know, I don't mean like I go to church on Easter. I mean, I'm a real Christian. I mean, I'm a sold out Jesus freak. I'm a Bible believer. I'm born again, and therefore I believe in the Genesis account of creation, and I don't believe in evolution. Now, the first time before I say that, I usually tell them that I usually ask, how many of you believe in evolution? And of course, almost everybody raises their hands. And then I say, how many of you believe in scientific or in creation, the Genesis account of creation? And it usually surprises me. Several people raise their hand in spite of the fact that they know they're in a distinct minority. And there are several people that don't raise their hands on any of them. And of course, you know, it's maybe they catch on that I'm onto something here. But anyhow, so then I tell them I'm a Christian and so forth. And then I say, so I'm using this word believe. And I say, I don't believe in evolution, that I believe in the Genesis account of creation, except I don't emphasize it like that. But then I ask them later, I say, now, before we get into this, can you think of a word that I've been using that maybe a little bit in excess. And almost every time somebody will say, yeah, you're using this word belief. So then I get into talking about what is belief. And a lot of times they say, well, it's something that's not a fact. And I say, well, okay, what is a fact? And they'll say, well, it's something that's true. So this is a progress that it takes. And I say, well, so what is truth? And then they'll say, well, it's something that is a fact, and as we get into this circular stuff, and then I'll say, well, so let's talk about truth. And so then I say, now, we probably cannot ever, all of us, come to agreement on what truth is. But we can almost always come to a conclusion about some attributes that truth will have. And so I'll say one of the first things about truth is it's the same thing. If it's really true, then it's going to have to be true in the past, in the present, and in the future. So truth is going to have to be the same yesterday, today, and forever. And then I say, and so I say, anybody disagree with that? And of course, everybody agrees with that. And I say, now, another thing about truth is that if it's really objective truth, it's going to have to be something that exists, whether you believe in it or not. And even if you refuse to believe in it, or if you believe in something opposite of it, then it's still the truth and you're wrong. Okay? So if it's really truth, then it's the truth. And so then I say, now, so generally I try to get off the subject of truth and I talk about science. Instead of saying that science cannot reveal truth, it's probably more directly functional to say that science will never help us to understand what is actually going on. That's the key issue. So science is a process that we go through where we take empirical data, we analyze the data, and we come up with principles and narratives. And these principles and narratives have to be consistent with one another in different branches of science. They all have to integrate together. And if they don't go together, then we have to make adjustments in the narrative so that it fits together. And so there's this big web of understanding, of scientific understanding. And we use that narrative to communicate how mathematical formulas work. Basically, that's what it boils down to. So there's a thing like Ohm's law. And Ohm's law says that with electricity, if you take the amount of current in amperes and multiply it times the amount of voltage in volts, you'll get the number of watts, which is how much work you can do with the electricity. So that is a principle that allows us to design machines, amazing machines, to do all kinds of stuff with electricity. And it's very successful. So Ohm's law is one of the basic principles of all of these electrical machines that we use today that are so magnificent. But then we have this narrative that says what electricity is. And the narrative is made up. It's a myth. And so the narrative starts out with a really crude explanation of what's going on. And then it gets more and more detailed as we make corrections to it. So now we have this story about electricity, light. In fact, I've got somewhere here. Gosh, I don't want to waste any time trying to find this thing, but I've got a PowerPoint slide, and I think it's posted. It's posted on, Bob, you have those files? Where are those files that the new people can download? So
if you go to participants, let's see.
yeah,
Chat. No, you have to go to chat. I'm sorry. If
yeah,
you go to chat, there is on the bottom, there's a place that says file.
yeah.
And if you click on that, David, you have to load them onto your computer so that everybody can download them. I
Well, I
couldn't do them.
already put them there. I
Okay.
put them there a couple weeks ago, I
Oh,
think.
did you? Okay.
Yeah.
Well, they should
So
still be there. Because this is the
So
same
you
number.
mean people are going to have to access my computer in order to be
No,
able to get those files? Okay.
No,
Well,
you
where
put,
are they? Are they on Google Drive or what?
I don't, that's a good question. This is something, this is something that
This is
I thought I was doing good last week when I was able to upload this file thing.
yeah. Okay. So
Where did-
let me just go over this. This is pretty entertaining when you get right down to it. So I ask my students what light is, and they'll say, oh, well, it's photons. And I'll say, yeah. And so then I'll ask them, well, what is a photon? And so they'll say, well, it's a little particle that behaves like a wave. And I say, how fast is it going? And they don't remember, but it's 300,000 kilometers per second. 300,000 kilometers. That's moving on. And so then I say, okay, so you're saying that this thing is moving 300,000, it's bouncing up and down like this. And they say, well, that's the way they draw it in the books. And so, and then I ask them, what is magnetism? You know, I talk about how you can take magnets in a vacuum and you can move and push them around like that, you know, without even touching them. And so I say, well, what is that in between the magnets that's actually doing that? And I say, well, that's a force field called magnetic flux. So then I start joking. I say, get out of here. What are you talking about? That's magnetic flux. So your physics teacher told you that's magnetic flux and you actually bought it? And so then I go through gravity and electricity, and they talk about the flow of electrons through a conductor. So I go over and turn the light switch on and off, and the light immediately goes off and comes back on. So I say those electrons are going up through that wire, and then if we pull the faceplate off and I pull the wire out there, which one of them is hot? Well, they usually say the white wire, and they're wrong. It's a black wire. And I say, so I can look at that wire. Where are the electrons? And if I touch it, I get shocked. Where are the electrons? What is going on here? So you can ask some really, really simple, basic questions about the foundational forces of the universe, and you can bring somebody to their knees in just a few minutes. The reality is we don't have the foggiest idea what is actually going on. We get an illusion that we know what's going on because we can control our environment so well. So science is really good at developing narratives to communicate how formulas and principles operate together, so that we can communicate how to build systems to manipulate the environment. And most of the time, these scientific systems work. I mean, we put these Volkswagen-sized things on Mars and run them around with a joystick. And it's just amazing. Now, the more successful we are, the more we get this illusion that we actually know what's going on. But we're not even getting any closer to knowing what's going on, because of the principles that scientific investigation is based on. So this last, I think it was the last talk I gave last week, I used a file, and I don't know. I uploaded it. I don't know where it went. It went in Neverland or something. But I have a PowerPoint that has a lot of these issues in it there that about how science works. Now I've also got a document. Let's see. I've got another document posted. I think I've got it posted, but it's let's see. Let me do a screen share here.
Failing to reject the null hypothesis is what you uploaded.
That's one of them. And here's another one here. Can you see this? Evolutionism versus scientific creationism on the limitations of science and the counsel of Scripture. This is a short one, but this talks about the importance of skepticism, what's happened to science, and some scriptural references. But that one on the null hypothesis talks about a lot of the problems with contemporary science. Okay, I need to get out of this screen share. And I don't see how to get out of the screen share. What have I done here? Oh, I'm not even in screen share. Okay, I thought I was in screen share. I'm still learning Zoom, sorry. See, one of the other things that has happened with science is back in 1957, when the Russians launched Sputnik, they launched the very first successful satellite to orbit the Earth, and that was Sputnik. And I was a teenager then, and I just remember everybody just getting the dickens scared out of them, because there was this pinko communist satellite over the United States going beep, beep, beep. And so then Kennedy said, okay, we're going to be the first, we're going to put a man on the moon in 10 years. And everybody thought, you're out of your mind. Well, he did it in less than 10 years. And he did it by throwing money at universities. And so the federal government started infusing tremendous amounts of capital into universities. And it resulted over time in a dramatic change in the enterprise of science, the way science works. And so when I was a youngster, scientists that I looked up to at that time they used real science, they used skepticism. But skepticism doesn't work today in the the money-based scientific enterprise. So like when I study science, I follow leads. And these leads are things, part of my discovery process, that lead me on to another investigation. But that is not a way to succeed in science today. So what you have to follow in science today is money. And you've got to be successful. You've got to write grants to get money. And then your grants have to be successful. So skepticism has been replaced with advocacy. So these are two opposing ways of dealing with information. And it has really corrupted science. And so like at the university, see, most science is driven by universities. And at the university, people who succeed in the culture of the university bring money to the university. And some of you may not know this, but like if I get a grant for $1 million from NIH, the university administration gets $500,000 of that money to go to the administration. They get 49.9% of the federal grants that come in. So see, this is the whole metabolism of the university is based on this influx of federal funds. And in order for me to succeed, if I was an assistant professor today, I would have to play this game, and I would have to bring money in to the university, because that is the measure of science today. So the best scientists bring in the most money. And they can't do that by following leads and using healthy skepticism in their analyses. So it's unfortunate. I don't know what to do about it. I don't have a solution for it, but it's something that people need to be aware of. That most of the research done in universities today is done to bring money into the university. That is its purpose and function, unfortunately. So, but it is not only has corrupted science. See, that's not what I'm talking about when I say that science can't reveal what's actually going on. Science can't reveal what's going on because of the way the scientific method is designed, the logic under the scientific method. And like last time I was talking about, or I think it was when I was giving my testimony, that I was teaching a course called biometry, and I was getting deeper and deeper into the scientific method because I wanted them to understand how science works. So I was studying the scientific method and the process and the logic, and I was beginning to come to the conclusion, because I went into this thinking that science could reveal objective truth. And the more I got into understanding how the scientific method works, the more I began to realize that this can never reveal what is actually going on. Not because we don't have enough money, not because we don't have enough staff, not because we don't have fast enough computers, but because it's impossible for us to figure out what is really going on by simply investigating empirical phenomena and drawing narratives about them that help us to design systems. And so that was a really difficult time for me. I went through, this was back in like the 80s. And I had a really hard time for about 2 years because I didn't even know what the worldview term, I never heard of that term. But I knew that mine was gone and I needed a new one. So this all happened to me well before I ever considered becoming a Christian. And,
David, can I interrupt you and ask
yes,
a question?
please do.
When you say healthy skepticism ceased to be a part of the scientific process, can you expound on that a little bit? Because to me, that's a big paradigm shift. It seems to me that a very good scientist would by nature be a strong skeptic.
Well, that a very good scientist would. Most scientists today are not, because they're chasing money.
So why is
well, okay. So here's the way it goes. So first of all, good science starts with weirdness. And if you've ever wondered why scientists are weird, that's the reason. So scientists are attracted to weirdness. And so what was that? Say, I mean, something's got to happen that surprises you, that's outside the box, and say, wait a minute, this should not have happened. Something happened here that doesn't fit into the way I understand things to work. So that's the weirdness that is supposed to start scientific investigations, because it's a lead, because it's something that doesn't fit into our web of understanding. And so we need to investigate it. We're compelled to investigate that. So then we say, well, let's see, it could have been such and such, or it could have and so, we go through this sort of brainstorming, judgment withheld, proposing a bunch of different things that like maybe it was little green men or something. And we come up with until we run out of ideas that might be a potential candidate explanation for this weirdness. And then we have to go through a process of attacking each one of those, trying to make them go away logically. And then we design our experiment around the candidate explanation that received the least damage from the skepticism. That's not the way science works today. So we propose an array of candidate explanations, and then we have to pick the one that we can get a grant with, or that we can, or that validates conclusions that we've had in the past, so we won't be wrong. And so science then today at that step, modern science fails skepticism, and it's converted into advocacy. So then after that, I designed an experiment, and this is what last time I went through this process of showing how you design an experiment. And there was a big fish kill, and I explained the process that I went through of investigating that fish kill. Now that's the kind of thing, that's the way science works best. And I didn't get grant money. I didn't get any grant money to do that fish kill study. And it changed the results of the fish kill study, changed the way we do things at fish hatcheries. Because a new technology had come in, it was lined ponds, and it had caused a massive die-off. And the reason was because they were using tetracycline, and now they had clear water, and it sunburned the fish. So now all across the southern United States where catfish are raised, they changed their policies as a result of this research. So see, what happened was I developed a new system and published it, and then in a journal that all the hatchery people read, and so that changed the policy. Now, I still don't know exactly what caused that, but I proposed that it was oxytetracycline in the presence of ultraviolet light, and I got results that were consistent with that, but that still is not a fact in the sense of a mathematical fact. Now, one of the other things I talk about in biometry is the various different kinds of facts. And, you hear, especially if you watch the news today, you hear all kinds of facts bandied around. But the two that I talk about are scientific facts and mathematical facts. So I remember when I got out of the service and went to college, I had to take this bonehead math course on remedial math, algebra. And I remember one of the things we had to do was we had to memorize the proof that the square root of 2 was an irrational number. And we had to go through this symbolic logic with using P's and Q's and M's and N's to prove that we will never find two integers that can be established as a ratio that will equal the square root of 2. Now that is a mathematical fact. The square root of 2 is an irrational number, but we didn't analyze any data. There was no data that went into that. Nobody went out and found a bunch of integers and tested them. It was symbolic logic. So that mathematical fact will never be challenged by new data. Whereas scientific facts are based on an analysis of empirical data. Data are always incomplete. They're never complete. The only reason we stop gathering data is because we run out. It's a deadline. We have deadlines that we have to publish, or we don't keep our jobs. So we're always basing our decisions on incomplete data, and then new data comes in, and we have to make adjustments, and then we change our narratives, and we change the way we do stuff. because of the new data that comes in. And new data are always coming in. And new data are coming in faster and faster today. And I think it's every year and a half or 2 years, information is doubled. And that's increasing at a faster rate. But we're not getting any closer to figuring out what's really going on. We're just getting better at handling the data we have at hand and developing systems that incorporate that data and to manipulate the physical environment. And science is great for information storage and retrieval. It's great for designing systems that work most of the time. It's great for medicine, although right now we're struggling quite a bit with this coronavirus. But, there's a bunch of scientists out there that are working towards a solution on this, and they're using principles of science, and they'll eventually develop a system that works. That doesn't mean we actually know what's going on. It just means we're able to control things a lot better. So I don't know if that answered your question, Bob, but the skepticism, the lack of skepticism is caused corruption in science today. But that's not the problem. That's not the reason science can't reveal truth. Science, under the very best circumstances, with the most rigorous, controlled experiment, can never tell us what is actually going on behind the green curtain, or whatever you want to think of it as. So and at the same time I was learning this, I was also, for some reason, learning about chaos theory and fractal geometry. And there's not much need to go into that right now. Well, maybe I could just show you some imagery here. Let's see, okay, share screen. And okay, so what do you see? Do you see this? Do you see this where my cursor is?
Yeah.
There's a very busy PowerPoint. Yes.
Yeah. Okay. All right. So these images here, like these ferns over here, would be identified by a pterologist, a fern specialist, as different species of ferns, like a New York fern or a bracken fern. I mean, they got their names, they got scientific names. But these images were produced by a very simple mathematical formula repeated over and over again. These are called fractals. These are called fractals here. These are fractals here that look like plants. This looks like a weed blowing in the wind. These designs here, these are produced. These look like scenes, and they're actually fractals. So the way these images are made is to take a simple random number generator and a very simple set of rules and iterate it over and over again to make these images. And because it's a random number generator, each time you run it, you'll get a different mountain range. But because of the input, it's going to have snow on the caps, and it'll have a certain slope here. So these are formulas that can be put into this, and it's going to make a mountain range that looks like this. And chaos theory has to do more with, I'll go ahead and stop sharing this now. Chaos theory has more to do with nonlinear systems, and it's the reason we can't predict the weather, even though we've been working on it for many generations. And this business about climate change and so forth, and combating climate change is an absolutely ludicrous prospect. It is just ludicrous once you understand chaos theory. So because the climate is based on convection in the atmosphere, and it is a chaos system, and it cannot be predicted ever. We can't predict the state somewhere down the road, and so it's also dangerous because, you know, if we try to combat climate change, then we're going to change the climate, but we're probably not going to like the outcome. That's a whole nother topic, though. But so at the same time, I was learning that science can't reveal truth. I was also learning about chaos theory and fractal geometry, and understanding how those images are produced. I began to realize, you know, I remember when I was a kid, I had bad eyesight, and so I didn't figure it out until I was in like the 8th grade. So Mom and Dad took me in and got me some glasses, and I went around like this. I just couldn't believe how well I could see. And I remember it was in West Virginia, and I remember it was in winter, looking up at the mountain, and the mountain was covered with trees that didn't have leaves, deciduous trees. And I just saw a gray fuzz until I put my glasses on and I could see the individual branches. And I was just amazed. And so I began to look at trees, and I noticed that I could look at a tree that didn't have leaves on it from a distance, and I could tell what kind of tree it was because of the branching pattern, the form and the branching pattern. I could tell what kind of tree it was. I didn't even have to get close to it. But that tree, that individual tree, was absolutely unique. There has never been one like it, never will be another one like it. But all of them have these features and it grows from a little tiny seed, you know, and with cell division and stuff. So that mystery there is that tree is a fractal. It has fractional dimensions. It's not a three-dimensional object. It has fractional dimension. And the process of producing that is a chaotic process that's guided by DNA. But DNA is not the blueprint of what that tree is going to look like. So I know I'm rambling here a little bit, but just trying to give you some background on where this comes from. When we look around and we see, like I look outdoors here and I see plants and trees and some structure on my house, we really don't know what's out there. And the more I understand about existence in this world, the less I know about what is actually going on. So don't get the illusion that just because we can do so many nifty things with science, that we actually know what's going on. The models that we use, some of you have been following the models that we use for the coronavirus. And people keep saying, why can't these people get it right? Well, the reason they can't get it right is because models are never going to work for predicting the future. They never have and they never will because of the nature of modeling. So what models predict best is the past. Models are great at predicting the past, but until you know the past, you can't predict it. In other words, you can't predict the past before it's in the past. But once it's in the past, then you can model it quite well. And now if things happen the same way next year, then you can predict what's going to happen, but that's because it's the past repeating over again. So we're only predicting the past, and that's the reason those models don't work, is because they're only good and only ever will be good at predicting the past. So now, if they're, what I would sort of like to do is to, we just got a few minutes left, is to answer questions that anybody might have along about anything I've talked about. And next time we meet, I'll I'll have something a little bit more organized, or at least I hope. I'm in the middle of finals too. I'm trying to get my finals written and stuff. So I'm probably not going to have much time, but I'll probably have enough time to put something together in the form of a presentation, and I'll be talking about maybe the scientific method or whatever. I've got a lot of things that I can talk about, but I'll try to put together like maybe the null hypothesis thing and talk to you about the hypotheses that are involved in the most rigorous kind of science that we can do, experimental science. And that is where you can understand that science can't reveal truth. Now, I want to warn you, though, that if you get with most people, especially academics, and you tell them that science can't reveal truth, you're not going to be able to argue with them. All right. And so it's going to take a while working through these issues on hypothesis testing to get you to where you can articulate why science cannot reveal truth and stand your ground in these discussions. So does anybody have any questions they'd like me to address, or future topics they'd like for me to cover?
Can you hear me?
Yeah.
I had some problems with my audio last week. I don't have any questions, but I do have a comment, and it just has to do with what you're saying about science not being able to reveal truth. You said that last week, and I wanted to disagree, because I've got a little bit of a background in science. It's been a while since I've been in a lab, but I was remembering what you said kind of brought something to my mind, and that is that we used to do all these sophisticated experiments, and then we would run our data through statistical programs, and if my boss said, well, what did you get? And I would get 0.997% truth. And he would say, that's not good enough. If you don't have 4 nines or maybe even 5 nines, that's not even good enough, but you still never get 1. You can never get to 1. And I think 1 would be truth. And it doesn't matter how many times we did the experiment, we would never get 1. It was impossible.
Yeah, but okay, here's the problem with that reasoning. And this is a very common misconception. So let me just ask you this. What does that probability represent? What is your understanding of the p-value?
Well, I would assume that's your confidence. It's your confidence that the statement that you're making or the hypothesis that you tested is true.
No, that's not what it is about.
Okay.
The p-value, and this is where I got the rug pulled out from under. The p-value, that probability that you were citing there of 0.99, that is the probability that random chance could have caused the outcome of your experiment. So what you are proving is that something is going on. Something non-random is going on. But you think that is pointing to the design of your research experiment. Now, see, so like when I did that Fishkill study, I came up with a hypothesis, a research hypothesis, that tetracycline interacting with UV light had caused that hyperphotosensitivity. All right, that was my research hypothesis. The p-value was off the charts. It was like 0.000001 or something like that, way off the charts. Very close to 1, probability of 1, that random chance was not the sole cause. So see, that is the best conclusion that you can come to with that probability. So you do this experiment, and then you go out and you announce, okay, the experiment was successful because random chance didn't cause it. Well, that's not a conclusion. So what you have to do is you have to go back to the experiment to look and see if there's any other way you can explain this other than the treatment variable. And failing to find anything, you reluctantly have to conclude, well, the best thing I can think of to explain this is the treatment variable I use in the experiment. Now, what is the likelihood that that treatment variable caused the outcome? What is that probability?
It's probably high.
It's unknown and unknowable. Unknown
Okay.
and unknowable. So see, there are actually three hypotheses involved in a successful experiment. There's the research hypothesis that you design the experiment around. That's what you have controls and a control group, a treatment group. You give a placebo to the control group and a treatment to the treatment group. Then you compare their means in a really simple experiment. And when you compare the means, if you get a good difference, then the null hypothesis rears its ugly head and says, you fool, don't you understand you can flip a fair coin 100 times and get 100 heads straight in a row? And you say, yeah, but it's not likely to happen. And it's not likely to happen, but it is possible. So in order to claim that we've got something other than random chance operating, we have to determine the p-value. So the null hypothesis and the alternate hypothesis are statistical. So see, when you ran a t-test, you've got the data from the control group, the data from the treatment group, and you ask the t-test, what is the likelihood that these two piles of numbers came from a common pool of numbers? And the p-value tells you the likelihood that those two response groups, two groups of response values, came from a common pool of numbers. But see, the t-test doesn't know anything about your experiment. It doesn't even know what your treatment variable was. It doesn't know anything about it. This is where my board came apart, when I realized that. So there is nothing about the p-value that points to the treatment variable or points to your conclusion. Your conclusion is a default conclusion because you couldn't think of a better explanation for it. So it's like when the opposing team doesn't show up for a little league match and you win by default. So every scientific conclusion is a default victory. Because, and now what happens is, when other universities run the same experiment and duplicate it, it doesn't even validate the experiment. It just validates the alternate hypothesis, which says that a random chance was not the sole cause. And then what happens is 10 years later, somebody gets some new data and they say, hey, wait a minute. We need to go back and look at this stuff again because we have a new way of looking at this now and we changed the narrative. And so see, those p-values don't have anything to do with the experiment. It just has to do with the likelihood that random chance could have caused the outcome. Does that help?
Oh, yeah.
Okay.
Absolutely.
Good.
Thank you.
Yeah, you bet. And this is, if you will read that, I'm assuming we can find that paper. I don't know where to look for it. I tell you what, Bob and I, let me tell you this, Scott. I will send this paper to Bob and he can email it to you. Okay. And it's a paper on the null hypothesis, and it shows you why there are 3 hypotheses in every experiment. And the 2 that you use in statistics don't have anything to do with science. They're not scientific at all. They know nothing about your experiment. They're just looking at the response values, and they don't know what the treatment values were. And if you read through that, that will help you to understand this and be able to articulate it a lot more. Yeah.
Okay.
Kyle, Finn, you guys have any questions?
No, I don't think I have any questions right now.
Okay. Okay.
You know, but I see what you're saying with the fact that statistics, it's based off of something that's completely separate than the actual experiment that you're doing, as
Yeah.
far as like the values of it. It has
Yeah.
no correlation to it. They're just applying a model to a system that they're working with.
Yeah. Yeah. It's what really got me was the fact that when I realized that every statistical hypothesis that I've run was only on the response values, the response variable. And it was just asking, what's the likelihood that samples with means this far apart could have come from a population that had or from populations that had identical means? And it had nothing to do with the experiment whatsoever. I was just busted by that. So I'll get that hypothesis paper to you, and Bob and I will figure out a way to get these papers made available to where you can download them and look at them. And then the idea would be to read through this and see if you have any challenges or questions about this, and then we'll just go over them next time. And because, see, interacting about issues in those papers will help you to be able to articulate this when you encounter someone else that you may want to engage in these topics with. So we're over time, aren't we, Bob?
Yeah, we're about 3 minutes over. So let's go ahead and conclude this time together. And thank you, David, for all that you have done here today. I want to thank each of you for being here. And this will conclude the meeting for today. I will, if you haven't given me your email, if you could send me your email to bob@cypresscreekchurch.com. If you could do that, I can send you a link to the recording of this video if you'd like it. So that'll be all for now. Thank you very much for coming.
All right.
Bye-bye.
Bye-bye.
Thank you, Dr.
Yes, sir.